Thanks for joining. Before I start, I want to thank my collaborators, Chivani, Janhui, Jenlin, Joel, and the many others that have contributed to this presentation. I want to tell you about how to accelerate deep learning workloads on OCP platforms. Let me start by giving an overview of AI training and AI inference. When you train a model, you take an input tensor and you pass it through a computational graph, also known as a deep learning model, and you get an output. In this case, it can be the probability of a pedestrian. This is called inference. When you're doing training, in addition to doing the inference pass, you compute an error between your actual output and the expected output. You know the expected output from the labels in the training images. And then you backpropagate this error through the computational graph or model in order to know how to adjust the parameters or weights of the model such that the model learns a better mapping from the input into the output. Now, when you're doing this weight update, often they can be small or they can be large. So you need to take into account the numerical format that you're using when you're doing training or when you're doing inference, which brings us to the next topic, the various types of numerical formats that are used in deep learning. The most popular format is called single precision, or IEEE floating point 32 bits, which you can see in the top. Now, this is commonly used for training and inference, but there is a push towards adopting lower precision, because then you can pack more multiplying and adds into your hardware. The most popular formats used for training at lower precision are bfloat16, or brain floating point 16, and FP16, or IEEE half precision. These formats have been shown to give comparable results as the single precision, or FP32. In addition, these formats can be used for inference, but for some models, you can do inference even with lower precision. Int8 has been shown to work successfully for multiple computer vision applications, such as image classification, and is often used in edge devices for inference, where power is often a constraint. At Intel, we have a number of products that can be used for training and inference, from general purpose CPUs to specific AI processors dedicated for training, such as the Habana Gaudi for data center training and the Habana Goya for data center inference AI workloads. In addition, we have other processors, such as the Movidios, which can be used for edge inference, where power is often a constraint, FPGAs, which can be used for low latency inference, GPUs, which we're developing for data center both training and inference, that can take into account AI as well as other workloads, and CPUs, which is going to be the primary focus of this presentation. Intel introduced the AVX512 instruction set in the first generation of the Intel Xeon Scalable processor. In the second generation, we augmented the instruction set with the AVX512 VNA9 instruction, which you can see in the top right. This instruction is able to fit in a 512-bit register 64 Int8 values, which is 4x more than the FP32 values that previously fit in the regular AVX512 instructions. This gives you 4x more throughput, which is beneficial in particular for inference workloads that can run with only 8 bits of precision. In the third generation, we'll be introducing a new instruction that will natively support bfloat16 multiply and accumulate. You can see this instruction in the bottom right. This instruction gives you a 2x more theoretical throughput over FP32. Now, in practice, during the training process, not all the computations are multiply and accumulate. So we've observed in an end-to-end training workload around 1.6x performance gain for training. For inference, the gain should be higher. In addition, the third generation of Intel Xeon scalable processors has up to 2x more cores than the previous generation, giving an additional boost in performance. Hive Solutions is developing the Catalina platform. This platform is based on the third generation of Intel Xeon scalable processors. It can be used for fungible compute for multiple cloud workloads, as well as specific deep learning inference and training, as well as for large data analytics. This design is built on an 8-socket server platform that can be scaled down to 4 sockets and can have interconnects with 100 gigabits per second Ethernet connections, thus allowing the end users to have this fungible compute platform that can support a wide variety of workloads. Now, with the second generation of Xeon scalable processors that has the AVX512 int8 instruction, we can see here some of the results for low batch inference, meaning batch size 1 inference on the popular model ResNet 50. You can see a 2.7x improvement over FP32. And this is already assuming that the FP32 software is optimized. For larger batch sizes, such as batch size 32, we can see an even higher gain of 3.3x. Now, when you're taking a model from FP32 to int8, you have to quantize the model. And there are some steps that are required in order to quantize this model. On the right, I want to show you the OpenVINO post-training optimization toolkit and explain how it works. You have a trained model, which is the output of your favorite framework, TensorFlow, PyTorch, or others, and you feed this into the post-training optimization toolkit. This toolkit collects statistics about the model and produces a quantized output, which you can see in the green cylinder to the right. And then this quantized model is passed to the OpenVINO inference engine. Now, on the left, I want to show you how the interface works. You have 2 ways to quantize a model. You can have the default way, and you can have a quantization-aware training. The default method attempts to quantize all the layers of the model that can be supported by your hardware and provides the maximum speed up in performance. But it may sacrifice accuracy beyond a level that is acceptable to the end user. We've recently added a second option where the end user selects the maximum acceptable loss in performance, in accuracy, that is acceptable to them, and then passes that to the quantization tool to get a model that performs within the accuracy that the end user expects. Let me quickly demonstrate how this works in a quick demo. In this example, I'm taking the MobileNet V2 model and I pass it to the optimization tool. You can see the accuracy is 90.69% at full precision. When I select the default int8 quantization method, and I'm only selecting 3 images to provide a quick result, you can see that the accuracy drops 0.4 points, and the latency greatly improves. But let's assume this accuracy drop is unacceptable to the end user. So then we select the other optimization method, accuracy aware, and we select an accuracy drop of 0.1%. And you can see that it's able to train a model that meets this accuracy. Now, the latency is better than the full precision latency, not quite as well as the default int8 latency. But here, this tool is providing a method to trade between maximum performance gain and minimal accuracy loss. Okay, now I want to show you some examples of the OpenVINO toolkit used across different types of workloads. On the top left, you can see the toolkit being used for road segmentation. On the top right, you can see it for image segmentation, where you can segment both the pedestrians and the motorcycle. On the bottom left, you can see it being used for text detection and recognition. And on the bottom right, you can see it for tumor classification. These are all running at full precision. Now, when I quantize the model and I run OpenVINO with only 8 bits of precision, you can see that you're still able to do the road segmentation, both the pedestrian and motorcycle segmentation, the text detection recognition, and the tumor detection with imperceptible difference in statistical performance, meaning they both provide very, very similar accuracy results. But yet, with Int8, we observe much better performance from all the way up to 2.7x in performance gain. So the model is running much faster with Int8 than FP32, and yet giving the same type of accuracy as FP32. Here you can see the configurations to reproduce the results, which you can get from the slides. And finally, I want to invite you to use Intel's optimizations in order to take advantage of these instructions that we've added to our hardware. You can see the instructions here on how to use TensorFlow, PyTorch, OpenVINO, and Python with Intel's optimizations. Thank you very much.
Okay, thanks for listening to the presentation. Feel free to type your questions. We have a few minutes left before the official session ends. Well, some of you are able to type some questions. Let me just tell you briefly a little bit more on the OpenVINO post-training quantization tool. I think this is a great tool to trade off between accuracy and performance. So as you heard in the presentation, we have new instructions in Xeon that are able to have much higher throughput using 8-bit multiplies accumulated to 32 bits. And however, some workloads suffer an accuracy loss. It's usually small, but sometimes it's unacceptable to the end user. And so with this tool, you can trade off how much you are willing to sacrifice some accuracy in order to gain this performance boost. Now, for some workloads, there is no accuracy loss, so you can have the full throughput without sacrificing any accuracy. In addition to computer vision workloads which you saw in OpenVINO, the instruction, the low precision instruction of intermultiplies also accelerate natural language processing models like BERT, for example. We published a paper showing that you can get good performance with 8 bits on BERT, as well as recommended systems. You can store the embedding layers with 8 bits. You can do some of the NLP layers with 8 bits. So you can do a lot of the workloads today in deep learning for inference with 8 bits. And as I mentioned, we are also adding 16 bits to be specifically in the format of bfloat 16 to our next generation of the unscalable processors, which we codename Cooper Lake, which will give you a performance boost and is very useful for training. With this numerical format, you can get the same performance for training as if you were doing the training with FP32 across all the workloads that we've tested. You get the same performance. Now, there might be outliers that might require FP32, but for the majority or for all the workloads we've seen, bfloat 16 works just as well without doing any hyperparameter tuning or any loss scaling and adjustments when you're doing the backpropagation. It just works out of the box. The last part that I wanted to highlight is, as I mentioned, the Catalina platform that's designed for multiple workloads. It's based on general purpose CPUs, but it has tremendous compute and is excellent for not just inference, but also training. So I invite you to check out more details on the Catalina platform. And finally, the last thought to answer one more question is the way to get the best performance on Intel scalable processors or in general on Intel CPUs is to make sure that you are using Intel's optimizations. And so in the slide, which should be available or soon to be available, you should be able to see the instructions on how to install the Intel's optimizations, how to use Intel's optimizations with the popular frameworks like TensorFlow and PyTorch, as well as with libraries that are popular in machine learning, like NumPy and scikit-learn. And we have a package with all the libraries that have been optimized for Intel, as I mentioned, the Intel distribution of Python. So with that, I don't see any more questions. I'd like to help you. I'd like to thank you again for your time, and we'll conclude the live Q&A now. Best wishes. Bye.